Now we go for question number 21. Question number 21 about series connection of cells. Series connection of cells. At present, let us consider series connection of only two cells. That series connection is made between points A and B. Okay? This is first cell having EMF E1 and internal resistance R1. This is second cell having EMF E2 and internal resistance R2. Correct? Fine. Now this series connection of these two cells is connected across some external resistance. Let it be capital R. Now what we have to do here? We have to find out current passing through this external resistance. Look, this is a single loop. In any single loop, remember, current passing will be same through all the components. So here through all these components, current passing would be same. Let it be capital I. Okay, fine. Now, in which direction will you show the current? Always away from positive terminal of the cell. Okay, away from this positive terminal, you can start this current, and that is capital I. Okay. Now here I want to make one point very clear, whether it is informed to you or not, irrespective of that, you please consider all these cells connected in series definitely, but in assisting manner, in an assisting manner. Then what is that assisting connection? I am showing you. Here negative terminal of first cell is connected with positive terminal of second cell. Negative terminal is connected with positive terminal, meaning thereby unlike terminals are connected together. And when unlike terminals are connected together, at that time that connection is called assisting connection. Correct? Whether it is told to you or not, every time in case of series connection of electric cells, you please consider those cells connected in series, but in assisting manner, in an assisting manner. Okay, fine. Now, in the direction of current, we just apply Kirchhoff's second law, that is sigma IR equals to sigma E. Correct? What we are supposed to do? We are supposed to take the product of current and resistance. Correct? But then, through the resistance, if your journey happens to be in the direction of current, then corresponding IR product should be taken negative. If opposite to direction of flow of current, then IR product should be taken positive. Correct? Let us see what is the case here. When you move this way, correct, in the direction of current, then IR product should be taken negative. Current is I, resistance is capital R, take the product I into R. Here it is. But because our journey is in the direction of current, I should take this product as negative. Correct? Go ahead this way, minus I R2, minus I R2, correct? Still our journey is in the direction of current only. Go ahead still, it is minus I into small r1, minus I into small r1, correct? How many such terms you will have? Equal to number of resistors. Number of resistors are 3, 1, 2, 3, correct? So you will have right now 3 such terms. Simple? Fine. Once again you go this way, correct, for sigma E, and when you go this way, correct, the terminal coming first in the way is negative, so you should consider this EMF to be negative on right hand side, because sigma E is on right hand side. Okay? So minus E2, correct? Go ahead, and when you go this way, the terminal coming first in the way is again negative, so this EMF is also to be considered as negative, so minus E1, correct? Multiply this entire equation by minus 1, then all the terms will be plus, positive. Okay? When all the terms are plus, after that you can take I common. Okay? From left hand side you can take I common. Inside the bracket it will be now capital R plus small r1 plus small r2. And here it will be E1 plus E2. Simple. Find out I now. transfer this bracket on the right hand side in the denominator, then it is E1 plus E2 upon capital R plus small r1 plus small r2, correct. Tell me, if you have third electric cell in series connection, in this series connection, if you got third electric cell, then what should be the change in this formula? Here you will have one more term plus E3, and here you will have one more term in the bracket plus small r3, correct. Had there been fourth cell, plus E4, here plus R4. In general, if n number of cells are connected in series, then what will be the current through the external resistance? From this, you can just generalize that result this way. Instead of E1 plus E2, you may think now E1 plus E2 plus E3 plus dash 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 plus En, and that entire summation you can write with a single term this way, sigma Ei, where I you must write well below E, correct, small and below, and that I indicates the order of cell, and that you should vary from first to last, from I is equal to 1 to n, correct. Divided by capital R as it is, plus what is this? Small r1 plus small r2. But in case of n number of cells connected in series, what we will write in this bracket? Small r1 plus small r2 plus dash 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 plus small rn, and that entire summation you can write with a single term, sigma small ri. I once again well below r and small n below, okay, and that indicates the order of cell which you must change from first to last, from I is equal to 1 to n, correct. Fine. Now, this is some sort of effective or equivalent EMF, which I indicate by this symbol EEQ, equivalent EMF, equivalent EMF. This capital R as it is, what is this? This is equivalent internal resistance. So, small r EQ, correct. I just specify here in place of what these symbols are used. I am showing you this EEQ is placed in place of this, correct. So, I am writing here EEQ means sigma EI from I is equal to 1 to n, and sigma EI means what? E1 plus E2 plus E3 plus dash 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 plus En. Similarly, small r EQ is placed for this term, and that is sigma Ri from I is equal to 1 to n. And how would you write in a, this long form? In a short form we write this way, but in a long form we can write this way, small r1 plus small r2 plus small r3 plus dash 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 plus small rn, correct. Fine. Remember this general formula, I is equal to effective or equivalent EMF divided by external resistance plus equivalent internal resistance, okay. Fine. Now we go for parallel connection of cells. Earlier it was series connection, now we go for parallel connection of cells, okay. In the figure you will find parallel connection of two cells. First cell has EMF E1, internal resistance R1. Second cell has EMF E2 and internal resistance R2, correct? Fine. How to find this first and second cell? They are connected in parallel between points A and B. Now here just I would like to make one point very clear, whether it is informed to you or not, you must understand in case of parallel connection of cells, the connection is made in an opposing manner, Then you may ask, why opposing manner? I am showing you. This positive terminal is connected with point A, correct? This positive terminal is also connected to the same point. So, positive with positive, correct? And here this negative terminal is connected here. This negative terminal is also connected there only. So, here negative with negative, positive with positive, negative with negative, meaning thereby like terminals are connected together. And when like terminals are connected together, that connection is called opposing manner, correct? These cells are connected in an opposing connection, correct? Here the connection was assisting and here connection is of opposing manner, got it? Please remember, in case of series connection of cells, the cells are connected in an assisting manner. In case of parallel connection of cells, cells are connected in an opposing manner. Got it? Fine. Positive with positive, negative with negative. Got it? And now this parallel connection is connected across some external resistance, let it be capital R, through which we want to find out the current passing. Okay? Now, from the positive terminal of first cell, the current emanating is suppose I1, and current emanating from positive terminal of second cell, let it be I2. This I1 and I2, they will add up at this point, and the total current is suppose capital I. And that total current capital I passes through this external resistance, which we require to find out. Okay? At this junction, these two currents associate to produce this total current, and here at this junction, this total current dissociates into two parts, I1 and I2. I1 flows through first cell, I2 flows through second cell. Simple. Now, in the direction of I and I1, I want to apply Kirchhoff's second law. Just consider this loop, look here, this one, in which I and I1 flow, correct? This is that loop in which currents I and I1 are flowing. Now, in the direction of I and I1, you please apply Kirchhoff's second law, sigma IR equals to sigma E, correct? Come on, go this way. Take the product of current and resistance. So, it is IR. But because our journey through the resistance is in the direction of current, corresponding IR product should be taken negative. So, I am putting minus sign. Go ahead. Come on. Here it is now minus I1 R1. Minus I1 R1. Correct? And in this loop, there were only two resistances, 1 and 2. So, we have got two terms. And now for sigma E to be written on right hand side, once again you move this way, and when you move this way, this way, this way, the terminal coming first in the way is negative. That is why this EMF even should be taken negative. Even is taken with negative sign, correct? And now multiply all the terms by minus 1, all the terms will become plus, and then it is IR plus I1 R1 is equal to E1. Find out I1 from here. How will you? First transfer this term on this side will become minus, and then after this R1 you can just put in the denominator on the right hand side, correct? So, I1 will be E1 minus IR upon R1. E1 minus IR upon R1. Got it? Fine. Similarly, if you consider this loop involving I and I2, correct? This loop, correct? Then you will get similar equation for I2. Instead of I1, you may write I2. Instead of E1, you should write E2. Instead of small r1, you should write small r2. This IR term will remain as it is. Okay, fine. But don't you know, total current is nothing but I1 plus I2. Total current I is nothing but I1 plus I2, correct? Because these two currents, they added and they had produced total current I. So, I equals to I1 plus I2. This I as it is, I1 plus I2 means this plus this. And when you take this plus this, you should take this plus this. But when you take this plus this, at that time, before taking addition, you just separate the denominator and then you write addition of the different terms. E1 upon R1, here are written, plus E2 upon R2, plus E2 upon R2. And now minus IR upon R1, minus IR upon R2. Take minus I common, inside the bracket capital R upon small r1, capital R upon small r1, plus capital R upon small r2, plus capital R upon small r2, correct? So, this plus this you can write this way, and now transfer this term which is right now negative on right hand side, transfer it on left hand side, will become plus, and after that you can take I common, correct? If you take I common from here, the term left from here inside the bracket would be 1, and when you transfer this will become plus, I already you have taken outside, then inside the bracket now it is capital R upon R1 plus capital R upon R2, correct? And on the right hand side you will find these two terms, E1 upon R1 plus E2 upon R2. E1 upon R1 plus E2 upon R2. Correct? I want this total current. Okay? Transfer this whole bracket in the denominator. Then it is E1 upon R1 plus E2 upon R2. Look here. E1 upon R1 plus E2 upon R2 divided by this entire bracket, that is 1 plus. Now from these two terms what I do, I just take capital R common. If I take capital R common, inside the bracket 1 upon small r1 plus 1 upon small r2. Give it equation number 1. Tell me, if you got third cell in the same parallel connection, then with EMF E3 and internal resistance R3, what the change you will make in this formula? You will add one more term here plus E3 upon R3, isn't it? And here also plus 1 upon small r3. Had there been fourth cell with EMF E4 and internal resistance R4, then here plus E4 upon R4, here inside the bracket plus 1 upon small r4. Got it? In general, for n number of cells connected in parallel, how would you write this formula in a generalized manner? I equals to E1 upon R1 plus E2 upon R2 plus dash 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 plus En upon Rn. And that entire summation in the numerator, you can write with a single term this way, sigma Ei upon Ri, where I you must write well below E, well below R, small n below, and that indicates the order of cell which you must change from first to last, correct? This 1 plus capital R as it is, but what is this? 1 upon small r1 plus 1 upon small r2, for n number of cells it will be plus dash 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 plus 1 upon small rn. 1 upon small r1 plus 1 upon small r2 plus dash 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 plus 1 upon small rn. That entire summation in a single term you can write this way, sigma 1 upon Ri. I indicates order of cell which you must change from first to last. Right? Be very careful here. In hurry, you know, students are making mistake. They write in hurry sigma Ri. It is not sigma Ri. It is not the summation of internal resistances. No, it is summation of reciprocals of internal resistances. Summation of reciprocals of internal resistances. That's why you must be very careful. You must write sigma 1 upon Ri. Okay, fine. And now, give it equation number 2. Now, again recall equation number 1. Equation number 1. From this equation, look, I am writing the same right hand side here also, correct? I have just made only one change. This capital R I have just multiplied here inside. Then capital R upon small r1, you can just check it, plus capital R upon small r2, capital R upon small r2, correct? Now, here in the numerator you can take LCM. It will be R1 into R2. R1 into R2. This R2 will be multiplied here, E1 R2, R1 will be multiplied here, E2 R1, correct? 1 plus R upon R1 plus R upon R2. Now you can take LCM in the denominator also. R1 into R2 will be LCM. This R1 R2 will be multiplied here, so it is R1 R2, and here R2 will be multiplied, so capital R into small r2. Here R1 will be multiplied, so it is capital R into small r1, correct? Now in this numerator and in this denominator, you can check R1 R2, R1 R2 will get cancelled. R1 R2 getting cancelled. And the remaining terms I have written here. E1 R2 plus E2 R1. Here it is. E1 R2 plus E2 R1 divided by R1 R2. Now again I can take R common, capital R common. Inside the bracket small r1 plus small r2, small r1 plus small r2, correct? Now just do one thing. In the numerator and denominator, you divide by small r1 plus small r2. Divide by small r1 plus small r2. Divide here. I have written here. Divided by r1 plus r2. Divide here. Come on. R1 R2 upon R1 plus R2. Here it is. R1 R2 upon R1 plus R2. And when you divide this term by R1 plus R2, left is capital R. Correct? Fine. Now, this current I have kept as it is. This capital R I have kept as it is. But what is this? This is nothing but equivalent internal resistance. of parallel connection of small r1 and small r2. If you find out 1 upon small r eq according to law of parallel connection, 1 upon small r eq will be 1 upon small r1 plus 1 upon small r2, and from that if you find out r eq, you will get it exactly this much, r1 r2 upon r1 plus r2, correct. For two resistances connected in parallel, remember effective or equivalent resistance is always in words multiplication upon addition, multiplication upon addition, only for two resistances connected in parallel. R1 into R2, that is multiplication, divided by R1 plus R2, that is addition, correct. So this will give me equivalent internal resistance of two cells connected in parallel, correct, fine. Now if I write current I in this format, correct, in the denominator I am writing equivalent resistance, here also R plus R eq. This is equivalent external resistance, this is equivalent internal resistance. Then tell me, if current is equal to something upon something, if current is equal to something upon something, that something in the numerator must be EMF, and something in the denominator must be resistance, equivalent resistance, correct. So if current equals to something upon something, and in that, in the denominator, if you are finding equivalent resistance, then that something in the numerator must be indicating some effective EMF. That effective EMF in this case I am showing by symbol EEQ, correct. Now just compare these two. If you compare these two, I equals to I, so this must be equal to this numerator must be equal to this numerator, that is EEQ must be E1 R2 plus E2 R1 upon R1 plus R2, E1 R2 plus E2 R1 upon R1 plus R2, correct. And this capital R as it is, but in place of this term I am writing small r eq. So this small r eq must be this much, R1 R2 upon R1 plus R2, correct. Mind well, at present we have derived these results for only two cells connected in parallel, correct. What about n number of cells? I am showing you. Just take now ratio, taking ratio of equation 3 to equation 4, this upon this, correct. Look here, this upon this, correct, EEQ upon REQ, here it is, EEQ upon REQ. But when you take this upon this, here on right hand side, R1 plus R2 will be getting cancelled, then left is this upon this. Come on, E1 R2 upon R1 R2 will get cancelled, left is E1 upon R1, come on, plus E2 R1 upon R1 R2, then R1 getting cancelled, left is E2 upon R2, correct. This is for two cells connected in parallel. Had there been third cell in the same parallel connection, then you could have got one more term here, plus E3 upon small r3, isn't it? Had there been 4 cell, plus E4 upon small r4. Had there been n number of cells connected in parallel, then the summation you can extend up to nth term plus dash 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 plus En upon Rn, correct. So why do you write in general this left hand side as it is, but on right hand side generalize that result, E1 upon R1 plus E2 upon R2 plus dash 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 plus En upon Rn, you can write with a single term sigma Ei upon Ri, where I you must write well below E, well below R. That indicates, come on, order of cell which you must vary from first to last, from I is equal to 1 to n, correct. And once again I remind, here if Req is the equivalent internal resistance of n number of cells connected in parallel, then 1 upon Req, according to law of parallel connection, you can write 1 upon small Req will be sigma 1 upon small Ri, where I is equal to 1 to n, correct. Remember, according to law of parallel connection of resistance is 1 upon small Req will be 1 upon small r1 plus 1 upon small r2 plus dash 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 plus 1 upon small rn. That entire right hand side you can write with a single term sigma 1 upon Ri, where I is equal to 1 to n. Be very careful, it is not sigma Ri, it is sigma of 1 upon Ri. It is not the summation of internal resistances, no, It is the summation of reciprocals of internal resistances. Got it? Please. Now we go for question number 23. Mixed connection of cells. Mixed connection of cells. See, in practice, if you have got n number of cells, correct, you can connect them in three different manners. Which three different manners? First method we have seen, that is about series connection. Second method just now we have learned, and it is parallel connection. Fine. But if you desire, you can still have one more option. You can connect them in a mixed type of connection. Why the word is used mixed type of connection, I will explain. Look here. Consider this mixed type of connection of electric cells. Okay? Look at the figure very carefully. Here I have shown some number of identical rows, among which this is first row, this is second row, this is third, fourth, fifth, and so on. Let this be last row, correct? Whether it is told to you or not, remember, in case of mixed connection of electric cells, all the rows are compulsorily identical rows. Identical rows. Whichever is the first row, identical to that is second row. Identical to that is third row. Identical to that is nth row. Correct? Nth row. Number of rows we will take m. Correct? Suppose number of identical rows is m. Correct? So why these all rows are identical? Look in the figure. Here in any row you will find n number of cells connected in series, and as I told earlier, in an assisting manner. Negative of first is connected with positive of second. Negative of second will be connected with positive of third, and so on. Correct? First cell has EMF E1, internal resistance R1. For second cell, EMF is E2, internal resistance is R2. For the last cell, EMF is En and internal resistance is Rn. Correct? And whatever is the first row, identical to that is the second row, identical to that is the last row. Correct? Fine. Now, all these rows are connected in parallel between points A and B. That's why it is called mixed connection, because in a row we find series connection, and in the entire connection we find all the rows to be connected in parallel. So there is a series type of connection also, there is a parallel type of connection also. That's why we call it mixed connection of cells. Correct? Let me remind you about that fact. I told you, in case of series connection of cells, whether it is told to you or not, irrespective of that, every time you must understand that all the cells are connected in series, but in an assisting manner. Here in case of parallel connection of cells, the cells are to be considered connected in an opposing manner. Correct? Positive with positive, negative with negative. Remember now? Fine. And here in case of mixed connection of cells, remember, all the rows have to be compulsorily identical, and all those identical rows are to be considered connected in an opposing manner, in parallel. Correct? Fine. Now, this entire mixed connection is connected with some external resistance. Correct? Let it be capital R, through which we are looking for current passing. Okay? How much amount of current will pass through this external resistance? That is what we have to find out. Look, current starting from positive terminal in the first row from this first cell will be like this, correct? Then through second row it will be like this, through last row it will be like this. All those currents will add up here and they will produce this total current. Okay? Let us find out. The total current formula, so far we have derived 2 times. The total current formula, general expression is this: I equals to EEQ upon R plus REQ. I equals to EEQ upon R plus REQ. Same formula we are using once again. I equals to, come on, E eq upon R plus R eq. Correct? But then, though the structure of the formula is same, but these two terms are different in different cases. Okay? What is this and what is this? In this case, I am showing you one very strange fact. You may find it strange, but it is a fact. What is that strange fact I am showing you? In case of mixed connection of cells, the equivalent EMF obtained out of entire mixed connection is just equal to effective EMF from only one row. You may be getting surprised, though so many rows are there, why the effective EMF out of entire mixed connection is just equal to effective EMF of only one row. Why it is like that? I am showing you. Suppose this cell is having EMF 1.5 volt, suppose, and in this first row there are 10 identical cells connected in series in an assisting manner. 10. How many? 10. What is the EMF of one cell? It is 1.5, and such 10 cells are there in an assisting manner. So 1.5 plus 1.5 plus 1.5, how many times? 10 times. It will be 1.5 into 10, that is 15 volt. How much? 15 volt. So what is the effective EMF between these 2 points? In the first row, it is 15 volt. But I told you, in case of mixed connection, all the rows are identical, and when all the rows are identical, whatever is the effective EMF from the first row, same will be from second row, same will be from the last row. So between these 2 points, what is the potential difference? 15 volt. Between these 2 points also 15 volt. Between these 2 points also 15 volt. Between these 2 points also 15 volt. And don't you know, for the components connected in parallel, the voltages will be definitely equal. So here is the case where you are going to get 15 volt in each branch. In each row, you are going to get only 15 volt. So finally, the potential difference between these 2 points will be also 15 volt. And what is that 15 volt? It is effective EMF from only one row. So remember, in case of mixed connection, though you may increase the number of identical rows, the effective EMF out of entire mixed connection will remain same. It will be equal to effective EMF of only one row. Got it? So this effective EMF out of entire mixed connection will be just equal to effective EMF only one row, and from one row how much effective EMF we are going to get? Just add up all these EMFs, because all these cells are connected in series in an assisting manner. So E1 plus E2 plus E3 dash 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 up to En, and that entire summation you can write mathematically shortly sigma Ei from I is equal to 1 to N, correct, where I indicates the order of cells, correct. Number of cells in one row I have taken N, correct. Number of cells in one row I have taken N, okay. This capital R as it is. What is a small Req? Try to understand this term now. This is equivalent internal resistance out of entire mixed connection. Wait. What is the equivalent internal resistance from only one row? It will be this plus dash 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 plus this. Why? Because it is a series connection where equivalent resistance simply summation of individual resistances. Come on, small r1 plus small r2 plus dash 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 plus small rn. And that entire summation you can write shortly with a single term sigma ri, where I indicates the order of cell, which you must change from 1 to n, that is from first to last, okay. But that is the equivalent resistance only from one row, and such identical rows are connected in parallel. How many? Total number of rows is m. Remember, when identical resistors are connected, in parallel, the equivalent resistance is single divided by number, single equivalent resistance, single equivalent internal resistance from one row is this much, correct, and divided by number of rows. How many number of rows are here? Total number of rows is m. That's why I am dividing by m. I repeat. What is the equivalent internal resistance from this first row? It is sigma Ri, correct? From second row also sigma Ri, from the last row also sigma Ri, because all the rows are identical. And remember, if identical resistors are connected in parallel, then the equivalent resistance is single resistance divided by number. Single resistance divided by number. Single resistance from any row is this much, divided by total number of identical rows is M. So I am dividing by M, correct? So this gives you formula of current passing through external resistance in case of mixed connection of cells. Okay, my dears, now one point is very interesting, super point I am showing you. Look here. If number of rows is increased in a mixed connection of cells, then look, suppose we are increasing number of identical rows, correct? Then you know what do we find? Current is increasing. This total current passing through this external resistance goes on increasing. Then you may think at the first sight that if number of rows is increasing, naturally we are using so many cells, and when number of cells is increasing, definitely this current will increase. No, my dear, here current is not increasing because of increase in EMF. No, EMF will remain constant. Just now I told you, in case of mixed connection, what is the effective EMF obtained out of entire mixed connection? Just equal to effective EMF obtained from only one row, and effective EMF only from one row is sigma EI, and it is same for all the rows, correct? So this does not change, this remains constant. Though we increase the number of identical rows, this remains constant, correct? Now tell me, this is constant, this external resistance is also constant, and then also this current is increasing, then it must so happen that this equivalent internal resistance must be going on decreasing as you increase the number of rows. Yes, that is the reason, that is the proper reason. See, when you increase the number of identical rows, M will increase. When M will increase, this term will decrease, because this appears in the denominator in this term. When M will increase, this term will decrease. When this goes on decreasing, this goes on decreasing, this entire summation will go on decreasing, and finally it will cause increase in this current, correct? So here, as you go on increasing the number of identical rows, no doubt current is increasing, but the reason for increase in the current is not the increase in the EMF. On the contrary, EMF is remaining constant. Then what is the proper reason? Proper reason is that the effective internal resistance of the entire mixed connection goes on decreasing. When this goes on decreasing, definitely this will increase, correct? That is the proper reason. Okay, fine. Now we go for question number 24. It is about Wheatstone bridge. Now what do you mean by Wheatstone bridge? Let me give you its introduction. Wheatstone bridge is a specific electrical network with the help of which we can find out unknown resistance. It is its physical importance. This electrical network was prepared in the year 1843 by Mr. Charles Wheatstone, and so in his memory we call this network as Wheatstone bridge, right? Now I am showing you its construction. Construction is very simple. Look here. We have one quadrilateral formed by connection of four resistances, one resistance in each side of this quadrilateral. Quadrilateral is this: A, B, C, D, A, and we find one resistance in each side, correct? Totally there are four resistances: R1, R2, R3, R4. You please show R3 here only, okay? Out of four resistances, one is unknown. Suppose R1 is unknown, whose value we have to find out. And other three, R2, R3, R4, they are known resistances, correct? Now after forming a quadrilateral out of these four resistances, what extra connection we have to make? I am showing you. We are supposed to connect one sensitive galvanometer across the two endpoints of one diagonal. What do you mean by sensitive galvanometer? It is that galvanometer through which even when very small current passes would show you immediately large deflection. The one whose response is very prompt and very large response, we call it sensitive galvanometer. Okay, fine. And then across the two endpoints of another diagonal, we are supposed to connect one battery and key. Correct? Fine. This entire network now onwards we will call Wheatstone bridge. Got it? Nobody will ask you about the definition of Wheatstone bridge, but just for your kind knowledge and satisfaction, I would like to give the definition. Look here. If a quadrilateral is formed by connecting one unknown resistance and three known resistances, and then after if a sensitive galvanometer is connected across the two endpoints of its one diagonal and battery and key are connected across the two endpoints of another diagonal, then the whole network is called Wheatstone bridge. Correct? Fine. Now, how we can find out the value of this unknown resistors? So, for that let us see the working of this device, working of this electrical network. On which principle its working is based upon? Let us see the working principle now. We now go for working principle. Total current starting from this positive terminal of the battery is suppose capital I. Okay? That current will come up to this junction. Correct? Fine. And further it will be divided into that many parts equal to number of branches. If there are two branches ahead, then it will be divided into two parts. Here there are two branches, correct? So, as many branches, that many parts. So, there are two branches, so this current will be divided into two parts. Let it be I1 and I2. I1 amount of current is flowing here in this branch, I2 amount of current is flowing here in this branch. Fine. Now, just assume that the electric potentials of these 2 points are equal. Then you may have a question, sir, how we can come to know whether really the potentials of those 2 points are equal? How we can come to know? For that purpose only we have connected this sensitive galvanometer. Suppose electric potentials of these 2 points are equal. Just assume. If they are really equal, then electric potential difference would be 0. And if there is no potential difference between these 2 points, then no current can flow from here to here or from here to here. So, in this branch, because of 0 potential difference between these 2 points, no current can flow. And because no current is flowing, then this galvanometer will not show you any deflection. At that time, the pointer in the galvanometer will just lie in the central position and it will indicate 0 deflection, correct? So, if there is no deflection in the galvanometer, you must understand there is no current in this branch, and when there is no current here, then it indicates that potential difference between these 2 points must be 0, and when potential difference is 0, potential values must be equal, correct? Now, this specific condition of this Wheatstone bridge in which the potentials of these 2 points have become equal, potential difference has become 0, and thereby no current is flowing in this branch, and that is why this galvanometer is not giving you any deflection. Such a specific condition of Wheatstone bridge is called balanced condition. What do we call it? Balanced condition. Here I have written balanced condition, or we call it equilibrium condition. Balanced condition or equilibrium condition. Okay. Suppose this Wheatstone bridge is in the equilibrium condition. Okay, fine. Now tell me, this current I1 will come here, but because there is no current in this branch, the same current I1 will continue to flow further in this branch. That is why here also I have written I1, correct? Because after coming to this junction, it is not getting divided. Okay. Similarly, this I2 amount of current will come up to this junction, but because there is no current in this diagonal, then the same amount will continue to flow further in this branch. because after coming to this junction it is not getting divided. Now this I1 and this I2 will add up at this junction and the total will be current I. Remember, in any circuit, current leaving the positive terminal of the battery and current arriving at the negative terminal of the battery must be equal according to law of conservation of electric charge. Okay, fine. Now, in the equilibrium condition or balance condition of this Wheatstone bridge, you just select two closed paths. One is A, D, B, A. A, D, B, A. Another is B, D, C, B. B, D, C, B. Correct? In both the closed paths, let us apply now Kirchhoff's second law, one by one. Come on. First of all, you take this one. Kirchhoff's second law, mathematical form, sigma IR equals to sigma E. We are supposed to take algebraic summation of products of current and resistances. Correct? Come on. You just move this way. A to D, D to B, B to A. Go this way. Correct? Now through the resistance, if your journey is in the direction of current, then IR product is to be taken negative. So minus I2 R3. Here it is. Minus I2 R3. Correct? Now go this way. Correct? Resistance of the galvanometer we have shown by symbol G. Resistance is there, but there is no current in this branch. So we are supposed to take product of current and resistance, but current is 0, resistance is G. 0 into G will be 0. Now further you go this way. What is the current? I1. What is the resistance? R1. Take the product I1 into R1, but because your journey is in a direction opposite to current, then IR product should be taken positive, plus I1 R1. Here it is, plus I1 R1. Correct? And now just remember, what is sigma E? Sigma E is the algebraic summation of EMFs applied in a given closed path. Right now, given closed path is this. Given closed path is this. Now, in this closed path, there is no battery, no EMF. That's why sigma E is 0. Correct? In whichever closed path you are taking algebraic summation of such products, in the same closed path we are supposed to take algebraic summation of EMFs. But in this closed path there is no battery, no EMF. That's why sigma E is 0. Correct? Transfer this, will become plus. So I1 R1 will be I2 R3. Come on, give it equation number 1. Now take another closed path, B, D, C, B. B, D, C, B. Go this way. There is no current in this diagonal. 0 into G will be 0. Go this way now. Minus I2 R4. Minus I2 R4. Correct? Why minus? Because your journey is in the direction of current. And now you are going this way. Direction of journey is opposite to this current. So IR product should be taken positive. Plus I1 R2. Plus I1 R2. And again, in this closed path also, there is no battery, no EMF. So sigma E is 0. Correct? Now transfer this. From minus it will become plus. So I1 R2 will be equal to I2 R4. Give it equation number 2. Now just take the ratio of equation 1 to equation 2. This upon this. Ratio of equations means ratio of left hand sides should be equal to ratio of right hand sides. This upon this will be equal to this upon this. I1 will cancel, giving you R1 upon R2. And here I2 will cancel, giving you R3 upon R4. Correct? Come on, R1 upon R2 equals to R3 upon R4. Here it is. R1 upon R2 equals to R3 upon R4. My dears, this is very important condition which is satisfied only in equilibrium or balance condition of a Wheatstone bridge. How would you express this condition in words? I am showing you. In whichever branch the current I1 is flowing, that arm of a Wheatstone bridge is called one arm of a Wheatstone bridge. In whichever arm current I2 is flowing, it is called another arm of a Wheatstone bridge. I repeat, this current I1 is flowing through this arm A to B to C, correct? It is called first arm of a Wheatstone bridge. Where I2 is flowing, it is this arm A to D to C. It is called second arm of a Wheatstone bridge. You just do one thing, you move in the direction of current in both the arms, and you please take the ratio of resistances. Okay? When you move in the direction of current I1, and if you take ratio of resistances, it is R1 upon R2. Here it is. And if you move in the direction of I2 in this second arm, and if you take the ratio of resistances, it is R3 upon R4. R3 upon R4. So tell me, what is this? When ratios of resistances taken in the directions of currents flowing in two arms of a Wheatstone bridge are equal, the Wheatstone bridge is said to be in the balanced condition. Okay? And now speak reverse. If given Wheatstone bridge is in the balanced condition, then ratios of resistances taken in the direction of currents in the two arms of that Wheatstone bridge must be equal. So situation is double implies. If this is true, then this is true. If this is true, then this is true. Correct? Fine. Now in this equation, if values of R2, R3, R4 are known to you, you can just put their values here. You can calculate and you can find out value of R1. That is how we can find out unknown resistance using this Wheatstone bridge. It is its use, its physical importance, that using Wheatstone bridge we can find out unknown resistance. Got it? But now tell me, when you will apply this equation, provided you know the values of R2, R3, R4. But how to make those resistances known? Just to make them known, we have prepared a specific Wheatstone bridge which is used in laboratory. Okay? Now what is that Wheatstone bridge which is used in laboratory? Let us see now. Wheatstone bridge used in laboratory. Okay? How this figure is prepared from this figure, I will just compare and I will just make you understanding. Okay? In the construction of laboratory Wheatstone bridge, we first of all take one wooden board, rectangular planar wooden board, and on that wooden board we just fix up three copper strips. They are, this is strip number 1, say this is strip number 2, say this is strip number 3. Okay? Then after we have some 9 contact terminals which are fixed on those strips. 1, 2, 3, 4, 5, 6, 7, 8, 9. How many contact terminals? 9. Okay? Which are also called studs. And then when you open that stud, you can insert the wire, you can just make it tight. That is called contact terminal. Okay? Fine. Now, what we do now, we just try to define different points. Now suppose this is point A, then any of these three can be taken as point A because all the 3 points are interconnected. Correct? Fine. Take this point as point B, then any of these 3 can be taken as point B because these 3 are interconnected. Take this point as C, then any of these 3 points can be taken as point C because these 3 are interconnected. Okay? Now tell me, what do you find here between A and B? Between A and B you will find unknown resistance R1. So this is point A now, this is point B, then between A and B we should connect unknown resistance, that is R1. Correct? Then what do you find here between B and C? It is known resistance R2. This is point B, this is point C. Between B and C we are supposed to connect known resistance R2. How it is made known in the laboratory? We just connect here some resistance box. RB means resistance box, in which whatever is the value of resistance you have kept, that you must be knowing, let it be R2. Correct? Then between A and C in this arm, instead of R3 and R4, we just connect between A and C, we just connect a long uniform resistive wire made up of an alloy called constant ton. Why we connect here wire made up of constant ton? Because for constant ton, temperature coefficient of resistivity or temperature coefficient of resistance is nearly 0. When temperature coefficient of resistance is nearly 0, what is the benefit you will get? Whether you perform this experiment in summer season or in winter season, whether temperature is high or low, irrespective of that, your final result will be almost unaffected by the change of temperature, correct? So, accuracy in the final result will be more provided you are using the wire of constant ton, okay, fine. It has uniform cross section throughout its length. Normally in the laboratory we have that sort of Wheatstone bridge in which the total length of this wire is 1 meter. 1 meter, that is why it is called sometimes meter bridge also. Whether you call it Wheatstone bridge or in this case meter bridge is one and same, okay. Now because this length is 1 meter, just to measure the length of any part of that wire, what we do in laboratory, below the wire and parallel to the length of the wire, we just keep some wooden scale in which the calibration is done in terms of millimeter, and then that wooden scale has got length 1 meter, we call it meter scale, meter scale. It is just kept below the wire and parallel to the length of the wire, okay. You can take the reading to the minimum value 1 millimeter, okay, fine. Now between points B and D, we have connected here, between points B and D, we have connected here common sensitive galvanometer. Similarly here also, one end of sensitive galvanometer is connected with point B, another end is connected with point D. But here just note one point very carefully, the second end of galvanometer is connected with a typical key. That key is such that you can just slide it on the wire, you can just make it touching at any desired point. Such a sliding key is also known as jockey, okay, it is called jockey or sliding key, fine. So because this terminal is connected to jockey and its position you can just change, that is why I am showing this sort of curved wire, correct, you can change this position, fine. Now let that point of contact of jockey with the wire, let it be point D, fine. Now between A and C, in the external part of the circuit, we find here battery and key. Then here also we must connect battery and key between points A and C. This is point A, this is point C. Between A and C now we connect one battery, one key, and we connect here rheostat as a variable resistor. We connect here rheostat as a variable resistor. Look, for this rheostat, this is fixed terminal and this is variable terminal. If you slide that variable terminal, its position will change. If you slide it this way, then this resistance will decrease, then current starting from battery will increase. If you slide this variable terminal this way, then resistance will increase, then this current will decrease, okay. So just to change the current passing through the battery, we need some variable resistor, and here we have connected in the form of rheostat, got it, fine. This is all about the construction of a Wheatstone bridge in laboratory. Now how to just proceed further, what is the procedure I am showing you. First of all, you just select any fixed value of known resistance R2. You can just take out some known resistance in this resistance box, okay. So this R2 is known to you. Then after, what you are supposed to do, you are supposed to touch this jockey anywhere along the wire, okay. When you touch it on the left end A, this galvanometer will just show you deflection on the left side. When you touch that jockey here, this pointer will deflect on right hand side, correct. Now what you are supposed to do, you are supposed to slide this jockey along the wire, and you must find out one such a point D where there is no deflection in the pointer of the galvanometer. Pointer should remain exactly at central position where the current passing through galvanometer has become 0. That's why it gives you 0 deflection. Correct? Fine. If you have found out that point D, where if you touch the jockey with the wire, then this galvanometer gives you 0 deflection, then there is no current passing through the galvanometer. And when there is no current passing through the galvanometer, then that condition of Wheatstone bridge is said to be in the equilibrium condition or balance condition. So this is how you are bringing this Wheatstone bridge in the balance condition. Fine. Once the Wheatstone bridge has come in the balance condition, then this typical point D is given 3 names. It is called null point or balancing point or equilibrium point. Null point or balancing point or equilibrium point. But the name null point is very famous. I have written here null point. Fine. Once you get the null point, you are supposed to measure this length AD. Let it be L1, and you must measure this length also DC. Let it be L2. Correct? Fine. Now what will be the resistance of this much length of the wire? Very simple. Resistance between A and D, it is R3. Resistance between A and D is R3. Correct? But how much is that resistance? Very simple to find out. Resistance per unit length of this wire is suppose K dash. You can give any symbol. Here I have given symbol K dash for resistance per unit length. For 1 centimeter, if the resistance is K dash, then for L1 centimeter length, what will be the resistance? K dash into L1. K dash into L1. I repeat, resistance per unit length is K dash, then resistance per L1 length will be K dash into L1. Simple. What is the resistance between D and C? Between D and C it is R4. Between D and C it is R4. Correct? And now it is the resistance of this much length of the wire, it is L2. Resistance per unit length is K dash, then for L2 length what will be the resistance? K dash into L2. Correct? Fine. And now because this Wheatstone bridge is in the balance condition, we can use this relation. Correct? Come on. Apply this condition for balanced Wheatstone bridge. R1 upon R2 equals to R3 upon R4. R1 upon R2 equals to R3 upon R4. What is R3? K dash into L1. Put it here. R3 is K dash into L1. R4 is K dash into L2. R4 is K dash into L2. K dash will cancel, giving you L1 upon L2. Correct? L1 as it is. But what is L2? Tell me the total length. Total length is L1 plus L2. But total length in a meter bridge, it was 1 meter, that is 100 centimeter. If L1 plus L2 is 100 centimeter, what is L2? 100 minus L1. So this L2 is 100 minus L1. Correct? And now transfer this R2 over here. Then you get R1 equals to R2 into L1 upon 100 minus L1. R1 equals to R2 into L1 upon 100 minus L1. Correct? You know the value of L1, you know the value of R2, then you can use this formula to calculate the value of R1. Correct? And then after what you should do, for other 3-4 values of R2, you can repeat this same procedure. Each time you can calculate R1, and then from the 4-5 observations whichever you collected for values of R1, you can go for finding average value which will give you best accurate value of R1. Correct? Fine. This Wheatstone bridge used in laboratory has got one limitation. What is that limitation? Using this Wheatstone bridge, you cannot measure very small resistance accurately. This fact gives you its limitation. Correct? Very small resistances cannot be measured accurately using this Wheatstone bridge. It gives you its limitation. Got it?